I will tell you sort of a rough summary and what I think are sort of important future directions, which for me are mainly related, motivated by physics. Okay, so, and then of course, so I guess, as I said, I'm not a mathematician. I'll probably say many things which aren't rigorous, but okay. So let's start with holomorphicity. So what is hydrodynamics? As I already said, hydrodynamics is the low energy limit of these various microscopic quantum field theories, okay? So what hydrodynamics really does is it encodes the conservation laws of conserved quantities. So basically, hydrodynamics is the long-range, long-time limit of the dynamics of something microscopic, and this is governed by conserved operators. So this is the conservation of the energy momentum tensor, which encodes energy momentum. You can also have some kind of charges. So then, for example, you'll have currents associated. You can have higher form charges. It doesn't matter. Whatever the conserved quantity in your system is, if it corresponds to a global symmetry, you'll have some kind of a current, and you should take it seriously in your effective theory description, all right? So at the lowest, sort of simplest way of describing what is hydrodynamics, it's an expansion. So you take your conserved operator, let's take energy and momentum, and you say, well, hydrodynamics is some kind of an expansion close to equilibrium. In equilibrium, we have some kind of temperature. And okay, a fluid should also be described by a velocity field. So what you do is you write down the most general possible expansion in gradients of velocity, which you promote to a field, and temperature, okay? So the general structure is something like this. So you have an infinite series in the energy momentum tensor, counting the number of derivatives acting on these fields. The fields are u and t. And then you assume that the derivatives of this are small. So then at each order, you write down all possible terms that you can that are compatible with some kind of structures that, like being close to thermal equilibrium, positivity of entropy production, and various things like this that you don't need to worry about. The point is, now, if you have such an effective expansion of energy momentum tensor, you can plug it into this evolution equation, all right? And you can analyze, so this is, now the conservation is the evolution equation. This is the generalization of what are called the Navier-Stokes equations, usually in fluid dynamics. So you can analyze this. You can go and you can study normal modes of this stuff. So you decompose in terms of Fourier modes, and you can solve, all right? So you can find these dispersion relations of modes, omega as a function of q. And the point is that in this classical hydrodynamics, which is an infinite order expansion, this thing you can write as an infinite series in powers of q, all right? That's the point. So we'll be analyzing this series for the first part of the talk. So for the simplest types of systems, there are two possible things that can happen. So for transverse modes compared to momentum, what you find is diffusion. So diffusion has the feature that for real q, this is momentum, for real q, omega is purely imaginary, okay? This is a purely exponentially damped mode. Sound, these are the longitudinal fluctuations, which I'm using to speak to you. So these have a real part, that's the propagation of my speaking, but because my sound doesn't carry to infinity, that's because there's also attenuation. So with sound, you find this alternating real part, imaginary part, real part, imaginary part, and so on, okay? So that's how this works. So this is hydrodynamics. This is, classical hydrodynamics. Now, for a lot of what we'll be talking about, this kind of stuff is extremely difficult to analyze in realistic systems. I mean, going to QCD, taking some kind of limit and calculating these coefficients is extremely, extremely difficult. But fortunately, we have a tool for analyzing some kind of toy models, and this is called holographic duality, which is a result of string theory. So basically, for some kinds of quantum field theories, which happen to be strongly coupled, that doesn't really matter, and for the simplest limit, they're in the large N limit, there's a dual calculation that you do instead. So you analyze some kind of usually 5-dimensional or 4-dimensional asymptotically anti-de Sitter black holes, and essentially what you do is you compute the quasi-normal spectrum, so the ring-down spectrum of gravitational waves, and this you can translate into the spectrum of your correlation function in QFT that you're interested in, okay? So it's a tool, it's a very useful tool for a set of toy models which don't exist, but they're very useful because they're close to what the kinds of things that do exist, hopefully, and we can actually do something, all right? So it's very nice because we can actually perform calculations, all right? Wonderful. So the most sort of kind of typical example that one can analyze is this maximally symmetric n equals to 4 supersymmetric Yang-Mills theory, which is a complicated QFT, but actually because of all the symmetries is really quite simple. So in this special large n, large coupling limit, this has a dual description in terms of the ADS black brane at finite temperature, and this is the spectrum that you get, okay? This is actually what the spectrum of transverse fluctuations looks like. There are these dots. These are the quasi-normal modes of the black hole. This is the spectrum of the correlator. And the lowest lying one, closest to the origin in the omega plane, this is the low energy one, okay? So this is the hydrodynamic pole. And then you can go and you can try to calculate this expansion. And this is the best that we've been able to do so far. So for sound, you get up to q to the 4th term. And then after that, due to reasons of troubles with multiple polylog integrals and so on, we don't have a nice closed form expression. The same goes for diffusion. Here we can also do the first 4 terms, and we can get to the q to the 8th term. What you can see, sound, as I told you, have real part, imaginary part, real part, imaginary. And for diffusion, you have all imaginary terms, okay? So this is a purely attenuated thing. All right, good. Now, very briefly, so recently, there's been a lot of interest in the field of high energy physics in quantum chaos. Why is that? Because, well, you know, at the microscopic level, there's mess. And essentially, beyond saying that something is messy, it's kind of difficult to really define what quantum chaos is. There are different definitions of quantum chaos, but people cannot really agree on what's the right one. And then recently, it kind of transpired that there's a nice observable for quantum chaos in these kinds of theories that I'm talking about. And these are something called out-of-time ordered correlators. You calculate some kind of 4-point correlation function of operators, and this grows. It grows exponentially, so it looks like this is, you know, something like quantum Lyapunov exponent, and it also spreads linearly in space, and you call that the butterfly velocity. Fine. So these also have some really beautiful properties. You can use sort of holography and some complex analysis to prove bounds on these things. You can also do similar things for systems that don't have holographic duals. That's not so important for this talk. What is important is that quantum chaos in all of these holographic theories that I'm talking about, so holographic meaning there's a QFT that has a dual gravitational description, okay? Which I am using because I am incapable of calculating what I want to calculate in any other theory, all right? That's just to be on the same page. So these have a very beautiful property. So if you have this infinite series, all right, so what turns out is actually that this infinite series has a property. It goes through a very special point. It's like a chaos point. So at imaginary momentum, so you analytically continue momentum, and then at imaginary momentum, there's a special value, which is at 2 pi t times I. This is the first Matsubara frequency, and also the Lyapunov exponent of these holographic systems. At this point, you can read off the butterfly velocity, right? So the whole thing resums into a function, which, if you evaluate at some special momentum, will give you the butterfly velocity that's actually secretly hiding in quantum chaos, all right? So what is special about this is actually if you calculate the structure of the correlation function like this, what you find is at these points, not only do you have a pole, but you also have a 0, okay? So these are special places where the correlation function is 0 over 0. So this means that their actual values, so they're regular function, but they're multi-valued. So it depends on how you approach this point. This we nowadays call pole skipping, because you have a pole, and then at some number of isolated points in the frequency momentum space, you have a 0. And anyway, so what we also found is that actually there's an infinite sequence of these points. Okay, so these correlation functions have poles, they have zeros, and at some points they overlap. And this always happens at an infinite set of multiples of these Matsubara frequencies. So these are thermal field theories. So it always happens at minus 2 pi t I times n, where n is a positive integer, okay? Okay, so later I'll use this. So just so far there's some special connection to quantum chaos, and there's some kind of an infinite set of constraints on all of these correlation functions that we don't understand very well from QFT, but we understand why this is happening from the gravitational dual point of view, okay? It's a bit of a funny situation. All right, good. So now let's get back to hydrodynamics. So very briefly, so you can sort of understand, how you solve these kinds of problems. So you find some function a, okay? This you get from the gravitational calculation, and then you have to find its zeros, all right? So this looks like, the usual kinds of problems where you're looking for spectral curves. So you have some p of x and y, where x and y are complex, and you're looking for solutions to this stuff. For example, you can have some very simple example. This is not particularly realistic, but you could have something like a, like a sphere. You treat this in a complex way, and then you can perform an analysis of this. Now, usually, of course, you can't find exact solutions, so what you do is you perform local analysis. Well, then you can look at what are the points along this spectral curve. So you find there are things like regular points. For example, here, there's a point 0 and 1. So what you know, if there's a regular point, then you know the first derivative of the function is non-zero. You use the implicit function theorem, and you can find the Taylor series, all right? That works very well. So there's a generalization to this, which maybe is a little bit less known. But you have what are called critical points of these algebraic or spectral curves, i.e. what can happen is that at certain points where you're interested in solution, let's say x star, y star is a solution, but also your first derivative is 0, and then let's say only the second derivative is non-zero, okay? So this is a critical point of order 2, and what you will find around such a point are two branches that are now expansions, typically, in square roots, okay? So you find two branches. These are called Puiseux series, and you find that, you can find these coefficients. Basically, the expansion parameter is x minus 1, because the critical point was at 1, to 1/2. So the expansion happens in fractional powers, and there are two such branches. Now, what we know is that these things converge. So they're convergent, and they converge at least to the next nearest critical point. Okay, in this case, this is 1 and 2, all right, for the two specific series. Now, what I say at least, it's a sort of a remark that one has to make. So these critical points are of two types. You have something called level crossing types of critical points, and you have level touching critical points, and there's been a lot of complaining about this. So what happens with level crossing critical points is that essentially when you go around this point, I'll show you later these examples. So the solutions exchange place like this. So let's say you go from yellow to yellow and blue to blue. Red is the critical point. As you go around this, they will exchange places. This is like level crossing in quantum mechanics, where you have energy levels of the harmonic oscillator, or well, not harmonic, but something more complicated. And as a function of the complex parameter or real parameter, they will exchange places. Okay, so this is level crossing. There are certain types of trivial critical points where nothing happens, all right? They just sort of go through. So these will not be particularly important. What limits the radius of convergence is level crossing, all right? Good. Now we continue. So as I said, these are the certain exactly types of problems that we have to solve at the end when we're looking for, let's say, the analysis of the spectra of these theories, and we're looking for the radius of convergence and so on. So what we're really solving here is some function, some p as a function of q. Now q in three-dimensional space is a momentum. So what you're actually looking at is q squared, because that's a scalar. So you're looking at pq squared, and omega is equal to 0, and you're looking for solutions, omega I, as a function of q squared. So in this simplest first-order hydrodynamics, this is the spectral curve. So it factorizes. So there's the diffusive solution which sits here, and because I'm working in 3+1 dimensions, it comes squared. And it multiplies another solution, which is the sound mode. Okay, so you solve this separately, and this is equal to 0. Now, you can analyze the critical points of this spectral curve. And let's say you find that at some points, p is equal to 0, so it is a solution. And let's say the first derivative with respect to omega is not 0, and so on. And only the pth derivative is not equal to 0. So this is some kind of a generalization of the implicit function theorem. Then you'll find that at that point, there should be p solutions, all right? Great. And what you know immediately, just because of the structure of hydrodynamics, just because of the way these things look, and you can see that these things are always Puiseux series, all right? So you know that these will always converge. They will always converge up to the next, at least to the next nearest level crossing critical point. Now, you can find the properties of these series. Something strange happened. You can find the properties of these series either by looking at the methods of Newton polygon, or what I like more and what I'll be actually using later is this Darboux theorem, all right? So there's a way to find the exponent of where the series blows up. So the series will blow up, or this solution will blow up at some point z is equal to 1 with some exponent nu, and we'll discuss this in great detail later. And you can basically find this exponent from a type of a limiting procedure, okay? So don't worry about this. So what is important so far is that basically just the structure of hydrodynamics and Puisot's theorem tells you that the hydrodynamic dispersion relations expanded in momentum space are convergent series, all right? They are convergent, that's it. So they're convergent up to where something bad happens to them, and this bad thing happening to them is essentially where this function smashes into something else, i.e. it collides with the next mode in the spectrum. So you have the infrared mode, then you look through this complexified frequency momentum space, somewhere this thing will crash into something else, and if this is a non-trivial critical point, a level crossing point, then this will set the radius of convergence of your hydrodynamic series, all right? All right, so let's look at this. So this is, again, the same. This is a diffusive model. It's n equals to 4 super Young-Mills. So you have the infrared mode here, and these are these higher modes, which we call actually the Christmas tree, because they look like a Christmas tree. Now what you do is you set some absolute value of momentum, you complexify it, and you change the phase. So you look at what this does. So, well, it draws out the circle as you change the phase, all right? Now you increase the absolute value of this momentum to 2.15, whatever. The hydro mode is now here. The gapped modes are here. So the hydro mode moves down. So they now do these kinds of little dances. Still, they have not collided, all right? It's still a closed circle. Then you come very close to the collision point. You see, they really attract. They look like some kind of, I don't know, planetary motions. Actually, you can associate a potential to this, and you can really treat this as motion of planets in some insane potential, if you like. Anyway, so they come close. They almost collide, but not quite. So the thing is still okay. Now you'll see, now you increase this absolute value of momentum even higher. And this is now after they have actually smashed into each other. And what you'll see is now the hydro mode will replace positions with the next mode in the spectrum, all right? So this is what happens now, you see? So the hydro mode started here and made a loop, and now it actually, so under the phase of 2 pi, it returned to the original position of another mode. So 2 modes merged into one path, all right? So this is what is called level crossing. So these are, again, this is the same thing. This is the diffusive thing. So the same happens for the sound channel, which I won't discuss in any detail here. But basically, at the collision point, where after that, the 2 modes, the hydro mode and something more ultraviolet, exchange positions, that sets the radius of convergence, all right? Good. So what is the solution to this? Well, not the solution, but the general statement of this is that hydrodynamic series are convergent Puisot series. So actually, diffusive modes are regular, so Taylor series in momentum squared. So they go as momentum squared because that's the variable to the n. So it's a Taylor series in q squared. And this is actually also the reason why you get only 1. And they all have the same sign. So the fact that they're all imaginary is also set by the Puisot theorem. What happens for sound is that you get 2 branches. So you have this plus minus, and this is because sound you can understand as p is equal to 2 Puisot series around the critical point, where critical point is the origin of this complex plane, okay? And the fact that they come with this plus and minus is also fixed by the Puisot theorem. In terms of physics, people sometimes talk about entropy, but it doesn't matter. So purely from the point of view of mathematics and structure of hydro, this is fixed. What is important is they are convergent. So now if you look at the complex structure of the dispersion relation, not in frequency, but in momentum space, this is what they look like, okay? So this is now omega for this diffusive mode, the shear mode. Shear is just another name for a diffusive mode, I guess. So if you look at this in the structure in the complex q squared plane, there's a holomorphic disk, all right? And this holomorphic disk is then obstructed by where the stuff collides into something else. And where it collides, they're basically branch points, and they're branch cuts going out of these places, all right? So there's a holomorphic disk. All right, so please stop me if this is getting confusing. Yes?
Can you go back a couple slides to the animation that you had?
Yes.
So what's the data that goes into this program? Like what do you have to...
You have to numerically solve the gravitational fluctuation equations. So you take anti-de Sitter 5 Schwarzschild black brane, let's say, yeah? You take general relativity with a negative cosmological constant, you perturb GR, you look at what are the fluctuation equations, you solve them, you impose infalling boundary conditions at the horizon, and you look at the asymptotics, and you impose Dirichlet boundary conditions at the end. So this is anti-de Sitter.
Just what does this program do, like this specific?
What does this do? It changes the phase theta from 0 to 2 pi of the quasi-normal mode spectrum. I don't know where I should start explaining. Can you help me? At what point do I start explaining?
Does it depend on just the data of a spectral curve?
Yes. Yeah, that's right.
And what's the form of that curve?
Oof. It's some infinite. You have to solve it numerically. Yeah, it's not an algebraic curve anymore. This is really just the full thing, yeah. And then you find the solution, and this solution, then you complexify it, and then you change the phase by 2 pi. Yeah. Practically, you get the spectral curve by doing a general relativity problem. So you do it numerically, okay? And these are the quasi-normal modes of gravitational backgrounds for complexified frequency and momentum. Okay? Is that okay? I can tell you more details later. It's not complicated. It's just numerics of an ODE. At the end of the day, you reduce everything to 1 second order linear ordinary differential equation. You solve it, you impose some asymptotics, and you get this. Yeah? So technically, it's not bad. I mean, even I can do it. I'm not very good at numerics, okay? This can be done in Mathematica in a few lines. Okay, good. So these are convergent, and one can actually compute the radius of convergence, even as a function of the coupling, and it looks like some kind of a curve. What is actually pretty fascinating, and maybe that's the important sort of take-home here, is that these radii of convergence are very large. Okay, so basically, naively, you might have expected that because when I constructed this series, my Q, which is really Q compared to the temperature, that there's a scale associated with equilibrium. So you would have maybe expected, or at least I did expect, that Q over T, which is the expansion parameter, should be small. So actually what happens is that it's pretty large. So this Q over T, what you typically find in these simple holographic models is, say, order 10, okay? It's not small. It's orders of magnitude bigger than what I guess I would have naively assumed before we did these kinds of analysis. And I think that, at least in my sort of view, this is sort of one way of making sort of precise that hydrodynamics is actually highly applicable way beyond the regime you might have naively expected it to be, okay? In this field, people use this phrase, unreasonable effectiveness of hydro, which just means that hydro works well whenever you try it. It's not a very well-defined phrase. It works well, for example, for quark-gluon plasma simulations and things like this, and this is one sort of incarnation of that. It has, at least in these models, it seems to have very large radii of convergence, okay? All right, good. Now, I think maybe in the interest of time, this isn't really necessary for what comes later, but I think given that this is a mathematical audience to some extent, it might be interesting. So I will just very briefly spend 5 minutes on this, and then I'll get to the reconstruction. So far we know that these hydrodynamic dispersion relations are holomorphic in some disk, okay? At least the disk. I mean, they're also holomorphic in some regions outside, but there is a holomorphic disk. They're also univalent. So what is univalence? Well, univalence is another property of complex functions, which I was not aware of until recently. So univalent functions are complex holomorphic and injective functions, all right? So they're injective, which means that f of z is not equal to f of z2 for z1 not equal to z2, all right? So basically, if you have a univalent function, I'm sure many of you know this much better than I do, what you can do, you can use this property to put very stringent bounds on such functions, all right? So holomorphic functions are stiff. These are even stiffer. So For example, there's some famous results in this business, like the growth theorem. Perhaps the most famous result is what is called well, it used to be called the Bieberbach conjecture, and then it's been proven by de Branches. And what you can show, or what he showed, is that if you have a function like this, defined on a unit disk, so f of zeta, zeta is the variable on the unit disk, you expand it in this way, you normalize the first coefficient to 1. There's a theorem that tells you that basically every single coefficient in this expansion must be bounded by n. All right, that's a really beautiful result. Looks like something you could give complex analysis students at, I don't know, for their homework, but it's not so simple to actually prove this. It's a very powerful statement, all right? I was not aware of this until recently. Nobody told me this in my class on complex analysis. So basically, every single coefficient for functions that have the property that are not only holomorphic but also injective is bounded both from below and from above by this beautiful integer, all right? So there's a simple example of this. It's the extremal function that works like this. It's called the Kobe function, all right? So this is zeta plus 2 zeta squared plus 3 zeta cubed and so on. This is what essentially saturates all the inequalities and so on, all right? So what is difficult in this business is establishing that something is actually univalent. So it's not so easy to prove that something is injective. It's not very practical to write a program and compare every single 2 points among each other and see if they're equal anywhere, and if not, you call it univalent, right? This is not very practical. So that's why in this business, people invent just probably hundreds, I'm not even exaggerating, different conditions that if you can show that this is true, then the function is univalent. So, of course, proving that something is locally univalent is not so hard. You just show that the first derivative is not 0. But proving that something is globally univalent is much, much harder, all right? So, but it can be done with certain special conditions like this. So for example, if you can show that the real part of the derivative of a holomorphic function is positive in any convex region of the complex plane, then this will imply that your function is univalent. So why am I telling you this? I'm telling you this because you can actually use this directly on hydrodynamics. So it turns out that these series are not only holomorphic, but they're also univalent. And if you take this into account, you can then, actually by doing some simple conformal maps, you can establish bounds on every single coefficient in this series, okay? This can be done. It's not very difficult. Basically, you find some kind of an inequality that your diffusion constant must satisfy, or the speed of sound, and every single subsequent coefficient in this series, all right? Now, one can analyze this, again, numerically in holographic models, and it turns out that this is actually true and that these bounds are quite powerful, okay? So you can look at some examples. This is for n equals to 4 super Young-Mills again. I don't have time to go into details of this. You can prove some statements if you have maximal univalence about how, for example, if it's maximally univalent, then the entire series must truncate exactly at the first order. These are the kinds of things that I've been interested in lately. Basically, the main difficulty in this business is really proving that something must be univalent. So injectivity doesn't come very naturally to a physicist, I think. Who cares if a function is injective? But apparently, I mean, it seems to be important, okay? So I don't have very good physical intuition for why some observable should be in an injective function. And I think that's sort of what's still missing in this story. If it's injective and we know the region of injectivity, then we can now prove all sorts of bounds on all of the coefficients of these hydro series. But proving that this is indeed true has been difficult, and that's something that I haven't been able to do yet. I have some ideas, but we'll see. But basically, it seems, though, from these numerical kind of experiments, that the properties of univalence are actually very robust. So far, the statement seems to be that either it's actually the entire holomorphic disk, which is univalent, or something will go terribly wrong at a local point. So if we now go back to this spectral curve, this is again my spectral curve for diffusion, what can happen is that this spectral curve develops a cusp or a self-intersection or something like this. In that case, you will locally lose univalence. And actually, that has physical meaning. So local loss of univalence means that the group velocity of your mode goes to 0. at some complexified momentum. And in that case, then you will lose univalence, and you can use that as the size of the univalence disk and then prove the bounds, okay? This is what seems to be happening. Now, I don't want to spend too much time on this. So with these complexified properties, I want to now make a statement about reconstruction of the rest of the modes, okay? And mainly what will be crucial for this is what I discussed before. So this Puiseux theorem and things like this, all right? So now let me tell you again the critical sort of mathematical parts of these statements that I'm using. So, all right, so the critical part of Puiseux theorem again, so you're solving some kind of an equation as a function of x and y. Let's say that this critical point is at 0, 0 for simplicity. So this is a solution, right? F is equal to 0. Now, the first derivative is not 0, is 0, and only the pth derivative is not 0. So by this, you expect that you will find p branches of solutions around the point 0, 0, which you can expand in this way, all right? So this is the general form of the expansion. Each of these p branches, so j goes from 1 to p, looks like this. So you have some coefficients, k, which start at k0, and they come with powers of k over mj, all right? Now, the critical part of this, so if mj is greater than 1, i.e., it's actually a fractional expansion, then the Puiseux theorem tells you that you necessarily must have mj families of such a solution that just essentially arrange themselves along the unit circle, all right? This was what I was doing before, remember, for the sound mode. So the sound mode came with these phases, e to the plus minus I pi n over 2, and as a result, basically, I found two solutions where the real part had an alternating sign, okay? There were two solutions. So this can be generalized to order p, and they will come in this kind of a form, okay? So you'll have, actually, for everything I'll do, only this p equals to 2 kind of solutions will be relevant, but this is a general statement that comes from Puiseux's theorem. Okay, good. All right, good. Now, how will I be analyzing these series, right? So there's a second thing called the Darboux theorem, which I already briefly mentioned, and I want to be more precise. So what does it mean? So let's say you have a function which is holomorphic in some disk. Something terrible happens to it at z equals to 1, right? It crashes into something else. So the theorem essentially tells you now around this point, there's a kind of a singular expansion. So f of z around this point z1 will go as z minus z1 to some exponent minus nu. So for the simplest examples, for me, this is a half. It's a square root, okay? This will be now accompanied by some regular function z of r of z at z1, plus some subleading terms, which are less sick, all right? They're less singular. Now, Darboux's theorem is essentially nothing but writing out this series around the critical point and using the original series and just matching the thing, and then making sure that this actually converges, that the errors, become smaller and smaller, and things like this. But basically, what one could show is that that one can reconstruct the coefficients. First of all, so one can compute nu, the exponent of this divergence, if you know the coefficients from the original series, and you take this limit, all right? So basically, the properties of the series around the critical point here, z1, are determined from the large terms of the original series, okay? Great. So if you know z1, you can then compute nu. If you know nu, I guess you can also compute z1, all right? Now let's say you know nu and you know z from this limiting procedure. You know the coefficients an. Now you can also compute all of the coefficients in the regular Taylor series of r of z expanded around z1. And this is just algebra. There's nothing profound about this. It's just matching and order by order, just matching the two series. So each coefficient Rm in the series can be computed from this limiting procedure again, from the coefficients an, all right, and from Rms at lower and lower orders. So you can iteratively build up all of the Rms from this series, like this. It's a simple iterative procedure. Then what we also showed, for example, you can do some multiplications of this. So you can, for example, isolate Q out. And we also derived a similar formula for Qm, which is an expansion of Q around Z1. Okay, so this, again, is just some algebra. This is also what we derived. I mean, equally easy as deriving Rm, okay? So nothing profound there. Good. Now, of course, in the simplest incarnation, the assumption is that you have only one critical point. But you don't usually have only one critical point. So for these holographic examples, you can have two critical points that limit the convergence. They can be complex conjugates of each other. They can just be two generic critical points. You can have one critical point that actually limits the convergence and another one that's nearby. Or you can have some generic J set of critical points. So what we did was we also derived all of the prescriptions for this. It's not conceptually any difficult. I mean, it's just, again, the same matching of series and doing some algebra, okay? So if you're interested, you can look at the paper. Now, for practical purposes, what do we actually want, right? So if you're going to be practical, usually you don't know the infinite series. You only know some certain set of these coefficients, all right? So let's say you know only a finite number of these coefficients, all right? That's one thing. There's another problem. So one problem with this limiting formula here is that it looks like you need to know either Z1 or nu, okay? That just knowing the coefficients of the series is not enough. But actually, in 1980, there was a paper written by Hunter and Guerrieri where they actually resolved this problem. So for practical purposes, this is not an issue. So you can define some complicated polynomials that are purely functions of your coefficients of the series. What you do is the following. So these are some recursively defined polynomials. You can analyze how they behave in the limit of large n, of the large coefficients. And what you can show is the following. So you take two of them. Now you have a set of two equations. And you can solve the set of two equations for Z1 and nu. You use this as a seed, and then you iterate at higher and higher and higher and higher orders of these polynomials. And in fact, this converges to the correct result for Z1 and nu. So basically, you don't actually need to know Z1 in order to compute nu. So you can get both of them from purely the coefficients of the holomorphic function expanded around the origin, all right? Good. So this is their work. So what we did then, they have a comment in the paper that says, of course, this can be done for higher coefficients too. But they don't say how. So we did have to do that. So we also derived these similar kind of polynomial equations that actually then also allow you, purely from the coefficients an, to compute RL. RL are the, remember, R's are the Rm here. These are the coefficients in the regular part of the function expanded around the critical point. All right? Good. So that can also be done. You can also do it for Q. And we also extend this algorithm for all sorts of different critical points, because sometimes they're useful. Great. Now, what is the statement? So the statement is as follows. So my claim is that actually a reconstruction of all modes in the spectrum, as long as they're connected by each other via level crossing, is possible by just knowing any one of them. So if you know the hydrodynamic series, let's say you know all of the coefficients, I claim that as long as all of the other modes in the spectrum, so all of these ones, then you can reconstruct everything out of this. Now, I think, probably this is obvious to people who have thought about this longer. I mean, people do this in resurgence, and they do it in reconstruction in position space. And it's usually wrapped in mystery of Borel and Padé and all this stuff. But I think it's all just the same thing, all right? So basically, as long as these things are some kind of resonances of the infrared mode, they all just know everything about each other. And in momentum space, where everything converges, you can see this very, very clearly. Basically, what these different modes in the spectrum are, they're different branches of the Riemann surface. So the whole thing is connected to each other by a Riemann surface, as long as they're level crossing modes. And you can see that this just works. So for example, there was also a paper before this in 2019 when Withers did this at an example. Also was a holographic example. And you could see that this worked for one of the modes. It was reconstructed. And there are a lot of other papers in position space, probably also in momentum space. I mean, this whole workshop is related to this. And I think so. I don't think that really, maybe this statement that I'm making is new in any way, but I think it's nice to state this. And I do think that there's a practical way of doing this, actually, sort of. Okay? So, all right, so how does it actually work? So in this language of what I told you, the way this works is as follows. So all right, so you have a series around the origin here. This is this series. Now, you know that something goes wrong. So where something goes wrong, now actually you can use Darboux to find all of the details of the expansion of omega 0. So this is omega 0 then expanded around the critical point Z1. And then, actually, because you know that this series came in powers of a half, then you use Puisot's theorem, and you know that the brother series must also exist. If you found the third, then you would know that there are two other branches of this, okay? So now, the other series, you just use Puisot, basically you just flip pluses and minuses, is the second mode expanded around the critical point, all right? So this, again, will have some of its, this will also be a convergent series. It will have some radius of convergence. And then you have to deal with analytic continuations inside the same sheet to go around and explore the values. So for these holographic models, again, I'm talking, this is n equals to 4 super Yang-Mills theory. It's a non-trivial, strongly interacting quantum field theory. You can see, I don't have a proof, but you can sort of see constructively that when you start from the first one, you can go to the second mode, to the next one, and then I don't see any reason why you couldn't just keep going, right? So this is actually, I find this conceptually quite fascinating, right? So it's really the infrared mode. So the infrared mode, fair enough, is expanded as an infinite series. So it has an infinite set of coefficients, but these coefficients really hide everything about all of the ultraviolet modes in that particular spectrum, all right? Good. So, example. So let's look at momentum diffusion for a three-dimensional CFT, which is dual to a stack of M2 branes, whatever. It's some kind of a special limit of what is called the ABJM theory. Anyway, it's a lot simpler than it sounds. It's just ADS for Schwarzschild perturbed, okay? So we look at this sort of practically. What can you do? So let's say you know numerically computed 300 coefficients of the hydrodynamic series, okay? So now I'm using the variable z. So what do you do in practice? As soon as you have these coefficients, you can actually analyze the radius of convergence. That's not so hard. You find where the radius of convergence is. Now, what you don't know is how many critical points there are at the boundary of convergence. Now, what you can actually, there are many ways to try to find out how many there are. There's one which is probably a complete blasphemy to mathematicians, but what you can do, you can just plot this function at the boundary of the disk, and you will see how many times it's blowing up, all right? And so if you do this for this case, you will very clearly see this is done as a function of the phase. It blows up twice, all right? And it actually blows up twice at complex conjugate values of this. So you can just guess, all right? It's an educated guess that there are actually two complex conjugated critical points. Now, if you make a guess that's right, then the Darboux procedure will converge. If you make a guess that's wrong, then it will not converge, and then you can try again, okay? So for this, it does converge. So what we find from 300 initial coefficients, the reduction in the quality of coefficients at the next order is about an order of magnitude, all right? So you get 12 coefficients which are satisfactory at this one level of reconstruction, okay? Now, what you can do, for example, then you can use this to calculate the gap. The gap is the value of the frequency at zero momentum. You use some kind of analytic continuation because the gap is outside of the radius of convergence of this Puisot series, but you do an analytic continuation and you can calculate the gap, all right? Now you can just continue. So you start it at the beginning, you go to the first critical point, you go to the second critical point, and so on. And you just keep reconstructing modes one after another, all right? So you do the same thing. Now the problem is, if you have only 12 coefficients, this just isn't good enough. You can't do anything useful. So what we do as a proof of principle, we just recompute more, okay? So we again compute 300 coefficients of this first series around Z1. And interestingly, we do the same thing. What you find then is that actually there's only one critical point on the boundary of convergence, but there's another critical point nearby. And for numerical procedures, it's useful to actually take into account both of them. It converges much better if you do it like this. And again, I mean, there's no law, it seems, but from 300, we again get 12. I don't know why this 12 is coming out. 12 are good, 13th is crap, okay? It just comes from 300 down to 12. I don't know. And again, you used an analytic continuation within the same Riemann sheet to calculate the gap, and so on and so forth. What is particularly nice about this is that it's kind of a detective-like thing. So you're essentially in the dark, and you have to explore the Riemann surface by doing analytic continuations, by using Darboux, and a sequence of these things, I believe, will reconstruct everything, okay? Good, so what is actually interesting is to compare this with the method of Padé approximants. So in this paper in 2019 for this holographic models where Withers did the same thing, he used Padé. And of course, Padé is the simplest thing that I would also try doing, because you can just use Mathematica and type in Padé approximant, and sometimes you get lucky, right? And so I think it's quite interesting to compare this. So we also used, again, 300 coefficients for this M2 brane thing. So what you find is, in particular, Darboux is extremely good at recovering the locations of critical points, all right? So if we use Darboux, we find the critical point Z1 to 18 significant figures. So with Padé, this doesn't work too well. So with Padé, you have to look at the singularities, and you have to decide on what is the accumulation point. And we couldn't do it better than to 3 significant figures. So that was really very bad about Padé, and an extremely good thing about Darboux, okay? So for this, for the actual procedure, if you don't know where the critical point is, then Darboux seems to be working much, much better. Now, what is actually amazing, so if, despite all this, you use both methods to just compute the gap meaning the value of the function at 0, with Darboux, you will get it to 2 significant figures, even though the location of the critical point is determined extremely well. With Padé, it just works magically. So even though Z1 is terrible, you get the value of the gap to 17 significant figures, because I think it's just by itself, it's already an analytic continuation to various other parts, so it seems to be really good at that. Now, what is maybe even more interesting is that if you actually do know the location of the critical point exactly, which is something that you seem to be able to do very well from Darboux, then Padé works actually spectacularly. So let's say we use the value of the critical point precisely, then the gap, by just using the simplest Padé from Mathematica, you get the right result to 26 significant figures, and you actually get 80 coefficients, not only 12, and all of them are computed correctly to at least 10 significant figures. So, I mean, unsurprisingly, I think it's the combination of these methods that is the best. And I find, at least because I'm not an expert, I find these numerical methods to be more of a art than science, because I don't know what to do. So I just try something else, and sometimes it works. I don't exactly understand all the details, and it's very hard to know what is the precise thing to do. It's kind of the same with solving ODEs that I found. So I think this combination seems to work quite well, actually. So is this useful? Is something that I would like to ask at the end. So I think conceptually, absolutely. It's conceptually very useful, because it really does tell us that all these modes in these quasi-normal spectra are related to each other. Okay, they're all just some kind of bizarre resonance of all of the other modes. Practically, maybe not quite yet, right? What you would want is, let's say, you compute the first 10 coefficients, and then to actually reconstruct lots of things out of that. And we are not really quite able to do this yet, okay? So, all right, good. So just as a final slide, and this I will not tell you actually how to do in detail, I think that this question of how much or how little you need to know about the spectrum can go even further. Okay, so far I told you that as long as all these modes are connected via level crossing, then you can just construct each one out of the other ones. And actually, it doesn't matter which one you know. And probably people who know a lot about complex analysis will just say, well, this is not surprising at all. Fine. So we also have, however, a new claim. So I think you need to know even less than that. So in these holographic types of theories, it seems that what is actually enough to reconstruct the entire spectrum is just these isolated sets of pole skipping points. So this works as follows. So you have a function, there's a diffusive function, this omega of q. It goes through an infinite sequence of isolated points. So we can show actually that if you know these points, then from that, you can completely reconstruct the entire dispersion relation. And from that, you can then reconstruct the ultraviolet parts of the spectrum. Okay, so I will not have time to tell you how to do this. The paper isn't out yet. It's fairly complicated, but just as a claim, I think that this question of how little you actually need to know about the spectrum is not quite resolved yet. So it's not. So one needs to know even less than one mode. Okay, you can know the values of this one mode at only isolated points, a discrete set of points, and then through some various things that you do in GR, and because these are holographic things, various things you do in GR, and then various analytic continuations, you can get the entire spectrum for these kinds of quantum field theories, okay? The details of this will remain for another time. So what is the summary? The summary is as follows. So these complex analytic structures are not just beautiful, they're not just very nice in mathematics. As you know, I guess I don't have to convince you this, they're actually very useful for trying to explore real things like transport, okay? And of course, there's a history of this very successful program of resurgence, and this has worked very beautifully. So what I was doing here is basically things that are a little simpler, just because everything converges. So in momentum space, everything converges, and you don't have to worry about divergences and things like this, or asymptotic series. But all of the same things, unsurprisingly, I guess, because it's just the same physics anyway. So if you do it in one space or another, I mean, who cares? It's the same physics. It just all comes out, okay? So it can all come out in this nice convergent way. What is important to stress here, of course, is that here I'm really talking about classical hydrodynamic things. So this doesn't include effects like hydrodynamic fluctuations or loop corrections to hydro and things like this. That is not yet understood, okay, from this point of view, certainly not. So I also told you about some new methods, which I think were not used before, at least not to my knowledge, of using the theory of univalent functions. Because these things in physics, they also seem to be univalent. And univalence is even stronger than holomorphicity. And you can use this to prove all sorts of rigorous statements for actual dispersion relations, and hence also for higher ultraviolet modes and so on. They appear robust and generic, but the exact connection with physics must be understood. So as a physicist, what you would like is to say something like, oh, this is a unitary correlator, therefore it must be univalent in this region. We like causality, unitarity, these kinds of things. Injectivity doesn't sit very well with physicists usually. So, okay, so this has to be better understood. And then I think the main statement, and I was trying to show you how to do this, maybe the statement isn't so surprising, but actually, so now we worked out all the details in terms of the Darboux theorem, how to do this, is that these spectra can be reconstructed, okay? So you can get from any one of the modes, hydro mode is the most practical because it's the infrared mode, you can go all the way from infrared to the ultraviolet, all right? Now, it's not only QFT, right? It's the same problem for quasi-normal modes and so on. These all obey and follow the same kind of equations, so you can just use it purely at the level of black holes and so on. So what needs to be improved is, as I said, the practical purposes of this. The statement, I think, is okay. What needs to be improved is the practical purpose given some very limited number of coefficients in this hydro series. And then, of course, what would be great would be if we can use these methods to also analyze, for example, Euler-Heisenberg, chiral perturbation theory, other things that are gradient expansions, for example, in momentum space. Can we get knowledge of ultraviolet modes from, I don't know, the photon self-energy, things like this. So I think these are kind of important questions that I would like to understand better in the future. Okay, thank you very much for your attention. This is from last night.
What is that?
It's just by Trinity. It was very nice.
Time for quick questions.
So you computed those poles in two different ways, the branch points.
Two different ways?
With Darboux and with Padé, right? If you go, yeah. That. You had two different ways of calculating
Like this
Z1.
stuff. Sorry, this?
No, you had like one was to up to 3 digits.
Sorry,
the other one.
yes, Padé and Darboux. Sorry, yes.
Yes.
Yeah, just to compare it. I mean, so I mean, if you know all the coefficients, then any method will be fine. The question is if you don't know all of them. Yeah. So yeah, this.
So I'm just wondering, like, how did you, just given Z1 to this 18 significant figures, how did you calculate a Padé? How did you construct a Padé approximant? Like there's two methods, and then just you say up to, like, you say that you can calculate it up to, or W1 of 0 to 26 significant figures. No, go down. Yeah.
Here.
Yeah.
So, well, you use 300 coefficients of the original series. Then here you know what is the value of the critical point. So you go to the critical point. Well, then you're already at that point. You also have to know that it's a critical point of order 2. Then you do this kind of, you introduce a new variable. This was all done here in this paper, Withers. You kind of just, you put the square root in by hand, okay? And then you have a Padé approximant for one of the branches of the square root. And you just, you type in Padé approximant in Mathematica and put some order 42, and out comes this. It's really very simple.
Okay.
It really takes 35 seconds to do the calculation, but it works amazingly well. It's really just Padé approximant at the critical point after you unwind. Because if you just do it in the original variable, you'll get nothing because it's a critical point. So the only little subtlety is that at the critical point, you have to put in a square root to unwind, because you know that you have two sheets of the Riemann surface. So it's very simple, yeah. But Darboux is much more involved. So if you're looking for practical ways of doing it, then Padé is, I guess, always the best because it's the easiest. But I don't know. Maybe people who know more about Padé know how to improve this step, how you actually reliably find the accumulation point of where the critical point is. I don't know how to do it. But maybe there's a way to, it looks like, oh, it's going somewhere, and now I have to decide it's here. Whereas with Darboux, it's a kind of a clearer way. I don't know. There might be methods that I'm just not aware of.
Any other questions? Thank you for the nice talk, Sasa. Okay, perhaps injectivity doesn't have a clear physical meaning, but do you understand the bounds on the coefficients physically, say similar to like eta over S or something like that?
Yeah. So what you need is the following. So you need to know the size of the region of injectivity that you can, so if these general observations are true, then this can actually be done by the radius of convergence. And then the only other thing you need to know is the value of the function at one point inside of the region of univalence, and that's it. So eta over S I don't understand, but what I do understand are these connections to chaos bounds. For example, there was a proposal by Mike Blake, how you relate diffusion to butterfly velocity and the butterfly velocity and the Lyapunov exponent. And actually, so if you pick this point, I didn't talk about this in any detail, the one point where you do know the value of the dispersion relation, if this is the pole skipping point, so the pole skipping point then directly relates you from hydro to the values of butterfly velocity and Lyapunov exponent. So Lyapunov exponent is business is trivial. It's always 2 pi t. So it's the butterfly velocity that's non-trivial, okay? And then from that, you can get these types of bounds. Yes, you can get them very precisely. So given some property of univalence plus pole skipping, you can get these types of bounds, for example. So the proposal was d is greater or equal to v squared over lambda with some order 1 constant. And you can get exactly these kinds of bounds, for example, for energy diffusion, for momentum diffusion, and so on. So that I do understand, yes.
Thank you.
you know, it's a precise way. It's not a generic kind of statement. But so you need some input, and the inputs are this: the size of univalence and the value of the function at any one point inside of this region. And that's all. Yeah.
Thank you for a very interesting talk.
Thanks. Yes.
So, two things to announce. One, we'll want to take the last picture of this program, I suppose. Last picture of the workshop. We'll take it in the lobby when we leave the room. And second is we'll start, Shia and Oliver will give the next talk, and we'll start that about 15 minutes late at 11:45. We have a nice long time for lunch, so that shouldn't be a problem. So come back at in half an hour at 11:45.